Hello, everyone. In this module 3, I will introduce the classification and regression tree, or CART. Specifically, I will describe tree-based methods for regression. This involves segmenting the predictor space into a number of simple regions. In order to make a prediction for a given observation, we typically use the mean or the model response value for the training observation in the regions to which it belongs. Since the set of splitting rules used to segment the predictor space can be summarized in a tree, these types of approaches are known as decision tree methods. Also, tree-based methods are simple and useful for interpretation. However, they typically are not competitive with the best supervised learning approaches in terms of prediction accuracy. Hence, in the next module, I will also introduce bagging and random forest method. Each of these approaches involves producing multiple trees, which are then combined to yield a single consensus prediction. We will see that combining a large number of trees can often result in dramatic improvements in prediction accuracy at the expense of some loss in interpretation. Here we go. Tree-based methods are conceptually simple yet powerful. Decision trees can be applied to both regression and classification problems. In this module, I will focus more on the regression problems. Basically, tree-based methods are based on these two main processes. First, partition the feature space or predictor space into a set of hyperrectangles. And second, fit a simple model, for example, constant, in each one. The 5 main characteristics are shown here, and the main implementations are CART, the classification and regression trees, and conditional inference trees with the R package, and decision tree with sklearn Python package. Here's a very simple decision tree example. When you wake up every morning, you always check the weather and decide whether you would stay at home or go to school and bring umbrella or not. For example, you are very likely to take umbrella if probability of raining is higher than 70%. Please take a look at this decision tree and understand the basic concept of how we would end up with each decision. As usual, we wanted to find a tree that minimizes some loss. For the classification trees, we have class probabilities at the leaves. For example, the probabilities will be in heavy rain in 90%. For the regression trees, we have a mean response at leaves. For example, the expected amount of rain is 2 inches. So this figure shows a simple decision trees with X1 and X2 predictors. So we usually restrict attention to recursive binary partition tree, which means splitting the data into 2 regions. And these are also easy to interpret. The Python provides manual visualization libraries for classification and regression trees. As usual, I have uploaded a deep note for producing these decision trees figure. So please check these deep note blocks and try to understand each decision tree. They are basically based on the same data, but they produce different visualization graph. Okay. So in CART, our observations start in one big group and are split into 2 subgroups. Each subgroup is then split into 2 additional subgroups until there are some minimum number of nodes in each subgroup or leaf node. The splitting is also based on some measure of homogeneity, similarity, or loss. I will explain this soon in later slides. In addition, since we are in supervised setting, the splitting criterion should be based on how well the new group estimates the response variable, the y. There is also another important difference. In CART, only a single feature is used to determine the split point. For this simple decision tree, we start from splitting one predictor variable into 2 regions. We call this very top node as a root node, and the green circles are called the parent node, and the red circles are called leaf nodes. Please note that as the number of leaf nodes increases, the complexity of the model increases as well. So we are trying to model the response as a constant in each region. This predictive value, the f hat, are determined from the regions, the R, and the if coefficients or score for the regions, the C here. Specifically, the coefficients C for the regression trees are based on the loss, and commonly used loss function is here the scalar loss. On the other hand, in classification models, the coefficients are vectors. K here indicate a different class or label. For this example data, we can calculate the C under bar M by calculating the mean of Y that fall into these red regions. And for the classification model, the coefficients for class 1 and 2 is 0.5 respectively, 0.5 and 0.5, because the probability for having class 1 and class 2 in this region is 50% and 50%. Here I have also attached another example. For this example data, a regression tree for predicting f hat here based on the x1 value, the x1. At the given internal node, the label indicates the left-hand branch emanating from the split, and the right-hand branch corresponds to the x1 larger than some value of t. For instance, the split at the top of this tree results in two large branches. The left-hand branch corresponds to x1 smaller than t1, and the right-hand branch corresponds to x1 larger than t1. So the trees has 4 internal nodes and 5 terminal nodes or leaves. The number in each leaf is the mean of the response for the observations that fall there. Here I brought some real-world data set, and I'm using the Boston house price data set to predict a house price based on the 5 predictors shown here. The RM, the average number of rooms per dwelling, and L stat is percentage of lower status of the population, and DIS is weighted distance to 5 Boston employment centers, and CRIM, crime, is the capita crime rate by town, and tax is full value property tax rate per $10,000. So in deep note here, please check the blog, see how I created this figure here. And this figure shows, let me go back. So this figure shows a regression trees fit to this house price data. It consists of a series of splitting rules starting at the top of the tree. So the top split assign observation having RM, the average number of room per dwelling, less than 6.94 to the left branch here. The predicted price for these houses is given by the mean response value for houses in data set with RM less than 6.94. For such houses, the mean house price is around $200K. And house with RM larger than 6.94 are assigned to the right branch. And then the group is further subdivided by the RM again here. Overall, the tree segments the house into 8 regions of predictor space with depths of 3. Next, in order to minimize our loss function, the CART uses a greedy algorithm to grow a tree. First, we split the predictor space into 2 pieces and model response Y in each region. By doing that, we can find the predictor J and split point T to minimize the loss function, and we can produce 2 regions. Right? Next, we repeat the process, looking for the best predictor and best cut point in order to split the data further so as to minimize the loss function within each of the resulting regions. and continue until stopping criteria met. For example, the minimum number of observation in region or loss function has minimal improvement. Once the regions R blah blah to Rj have been created, we predict the response for a given test observation using the mean of the training observation in the region to which the test observation belongs. Okay, let's go back to the Boston house price example. Please notice in the figure 3 for the Boston house price data that the first split was based on the average number of room per dwelling, the RM. Specifically, if an RM is less than 6.94, they go down left side, otherwise they go to the right side. Let's examine this first split in more detail. So if you look closely into the first split of the root node here, we can find this skid plot here. The point 6.94 is basically here basically a univariate change point model. This split point is best change point using a Gaussian model. Alternatively, the reduction in MSE or SSE, the sum square error, is maximized by splitting at this point and fitting the data on each side of the split with a constant. Here's some detailed mathematics. So if you are interested, please pause this video and try to understand them. Basically, we want to find the optimal splitting point that minimizes the loss function, the error sum of square, the SSE, or maximizes the gain after splitting the data into two regions. Right? So before splitting the data, we can calculate the SSE by using this equation. And after splitting the data, we can calculate the SSE for left and right regions. And finally, we see how this updated SSE and gains change with respect to each split point. Let's see how the updated SSE and gain changes now. So these two figures show how the updated SSE and gain change with respect to different splitting points for the RM predictors. So here's the splitting summary. So for each iteration, we calculate the gain loss for R feature and R possible points and choose the pair that maximize the gain or minimize the overall loss. A J star here is the features that maximize the gain, and the star is the split points that maximize the gain given the J star. So how can we decide the size of the tree? So deciding which tree models to use is very important, and it again involves the bias variance trade-off concept. Please watch the bias variance modules if you have not watched it. And first, a large tree, the many leaves node with few observations, can overfit, but a small tree cannot capture important structures. As you can imagine, the tree size is a tuning parameter governing the model's complexity, and the optimal tree size should be adaptively chosen from the data. Now we can use an early stopping technique actually, and the early stopping means splitting when loss function has insignificant improvement, like for stepwise. However, a seemingly worthless initial split can lead to a good split further down to the tree. There is also another interesting method called pruning, and it is about growing a full tree, prune back. If you're interested, please refer to this website. And furthermore, one of the very interesting applications of tree is that it tells you the importance of feature in your data. These are several ways to measure the importance of a feature in a tree. Here are only a few. So a tree can tell you the importance by measuring the number of times the feature was used to do a split. In our previous example data, the RM may be very important variable in predicting the house price. And it can also measure the importance of the tree feature by calculating the total reduction in loss of all the splits made by the feature. And there is also a permutation-based importance. It reruns the tree but include a permuted version of the feature. Any decrease in performance indicates the feature was important. So decision trees for regression and classification have a number of advantages over the more classical approaches. First, trees are very easy to explain to people. In fact, they are even easier to explain than linear regression. Second, some people believe that decision trees are more closely mirror human decision making than do the regression approaches in previous models. Also, trees can be displayed graphically and are easily interpreted even by a non-expert. And it can be robust to outliers in feature space and more. But there are also some limitations to trees. It can be unstable due to a greedy hierarchical structure, which means one change at the top split can change the remaining trees. And it would be difficult to use trees for making inference due to stepwise search. And trees generally do not have the same level of predictive accuracy as some of other regression and classification approaches. Lastly, trees can be very non-robust. In other words, a small change in data can cause a large change in the final estimate tree. However, by aggregating many decision trees using methods like bagging, random forest, and boosting, the predictive performance of tree can be substantially improved. I will introduce this concept in next module.